Hello dear students, welcome you all. How's everyone? Are you able to hear me? Are you able to see me? क्या आप लोग सुन पा रहे हैं, देख पा रहे हैं? Anyone online? If anyone is online, just say hi. Okay, so let us start our session. So in this session we are going to discuss ESE prelims, previous year's questions. These previous year's questions are going to help you in ESE examinations as well as in GATE examination, because if you solve previous year's questions of GATE examination, you will find very limited number of questions, because only 65 questions are asked in a year, and that too all the papers combined. But in engineering services, 300 questions in prelims are asked every year. So there is wide variety of questions, large number of questions you will be able to find. So if even if you are preparing only for GATE, if your target is only GATE examination, then also I will advise you solve ESE prelims questions also, as well as if you solve ESE conventional previous year's questions, you will be finding a lot more concepts are getting cleared when you are solving conventional questions. Okay, so right now in this session we are going to discuss ESE prelims question. Good evening PK Entertainments. Okay, so let us start the second lecture, Properties of Materials 2. My name is Anirudh Singh Rathore, and in today's class we will be discussing ESE prelims question of chapter 1 from year 2000 to 2006. All the questions that were asked from this chapter from the year 2000 to 2006. Okay, so first question, match list 1 with list 2 and select correct answer using the codes given below the list. Okay, so these questions will also help to revise all your concepts. Okay, some questions are easy questions, some questions will be very good questions, some conceptual questions will also be there. So easy question will help you to revise, and conceptual questions will help you to build your concepts. Okay, so this is the match the following question. Okay, let us see. Tenacity will be ultimate strength and tension. Okay, so for A, option 2, statement 2 will be the correct. Plasticity means continues to deform without much increase of stress. Okay, there is deformation is continuing but stress is not increasing, that is plasticity. And ductility is ability to be drawn out by tension to a small section without rupture, right? So correct answer for ductility is statement 4. And malleability, extension in a direction without rupture. So when we will a discussion on principal stress problems, so principal stress I teach at number 4. Okay, chapter number 4. So you continue the series, principal stress will also come, and I will be covering entire strength of materials, PYQs. Okay, so chapter 4 will also come, principal stress will also come. Okay, focus on this now. Malleability, extension in a direction. So malleability is under compression, no? How we are saying that it is extension in a direction? So when we are compressing, okay, like this, so in this direction it is compressing, but in some other direction there is extension also. Okay, so based on the current options, the best suitable answer for malleability will be 3 only. Okay, otherwise will not be getting any matching answer. Okay, so the remaining option for malleability is this only. Okay, so correct sequence will be 2 1 4 3. So 2 1 4 3 will be the correct answer. Option A will be the correct answer. Got it? Okay, let's move on to the next question. Question number 2. A steel bar 300 mm long and having 24 mm diameter is turned down to 18 mm diameter for 1/3 of its length. Okay, so actual length of the steel bar will be, original length of the steel bar was 300 mm and diameter was 24 mm. So for 200 mm length, the diameter is remaining 24 mm, but for 100 mm, this diameter is reduced, turned down in lathe machine, probably in lathe machine. Okay, and it is turned down to 18 mm diameter. Okay, so this length. Okay, now before drawing the supports, let us see what else information is given. It is heated 30 degree above room temperature. So we have heated this bar, entire bar, 30 degree above room temperature, clamped at both ends. Then after heating we have fixed at both ends. Okay, so after heating we have clamped at the both ends. So now the length is little bit increased, length is increased. Okay, and then we have clamped it and allowed to cool to room temperature. So now after clamping, what we are doing, we are reducing the temperature. When after clamping we are reducing the temperature, what is happening? Which type of stresses will be introduced? Tell me. After clamping, when we are reducing the temperature, which type of stresses will be introduced? They will be tensile stresses or compressive stresses. Come on fast, answer me. Okay, so this length is 200 mm, this length is 100 mm, and here the diameter of part 1 is 24 mm diameter, and diameter of part 2 is 18 mm diameter. Okay, so here 18 mm diameter. This is, let us say this is part 1 and this is part 2. Okay, tell me, a very easy question. After clamping, after fixing both the ends, now I'm reducing the temperature. Which type of stresses will be introduced? Now when after fixing I'm reducing the temperature by 30 degrees Celsius, this bar has tendency to reduce in its length. Okay, so tendency of the bar is to reduce the length, but these supports will not allow the reduction in length, so they are trying to pull the bar. They are pulling the bar to maintain its original length. So when these supports are pulling and bar wants to shorten, we are getting tensile stresses. So there will be tensile stresses generated in the bar, right? Now if the distance between the clamps is unchanged, yes, the distance will be unchanged, fixed supports, the maximum stress in the bar is, so we have to calculate the maximum stress in the bar. Coefficient of thermal expansion is given and Young's modulus is also given. Okay, so considering all this information, we have to calculate now what is the maximum stress in the bar. Okay, now in this part and in this part, stresses will be same or different? In part 1 and in part 2, stresses in part 1 and stresses in part 2. So stresses in both the parts will be same or stresses will be different in both the parts? Just think and answer. Stresses in part 1 and part 2 will be different. Why? Because the force, resisting force, will be same in both the bars. Okay, so whatever force is there, the force will be same. Okay, so if this end is pulling by force P, this end will also be pulling by force P. So in this bar, everywhere there will be a tensile force P, and in this bar also, in this part also, there will be tensile force P. Okay, so in this bar also tensile force P, in this bar also tensile force P. So tensile force is same in both the bars, but area is different, and when area is different, the stresses will be different. Okay, so force is same in both the bars, but stresses will be different. Okay, so if I want to know the ratio of stresses in both of them, what I can do, the force equilibrium will help me. Okay, so force in bar 1 will be equal to force in bar 2. That means sigma 1 into A1 will be equal to sigma 2 into A2. Yes or no? Sigma 1 stress into area, that is force, and stress into area, that is again force. So forces are same, that means sigma 1 A1 will be equal to sigma 2 A2. Now sigma 1 into A1 will be pi by 4 into d square, pi by 4 into 24 square, that will be equal to sigma 2 into pi by 4 into 18 square. Okay, now pi by 4 will cancel out, 6 into 4 square, 6 into 3 square. So here we will be left with 4 square, here we will be left with 3 square. 4 square means 16, 3 square means 9. Okay, so that means sigma 1 will be equal to 9 by 16 sigma 2. Okay, so this much. I hope till this point everything is clear to you. Okay, so now let's move on to the next part. In the next part, what I am going to do, I have to use compatibility condition. Here the forces are same, okay, but stresses are different. So in order to calculate what is the stress, I need to have one more equation. So that equation will come from compatibility condition. Now what is the compatibility condition? Change in length of this portion of this bar will be plus change in length of this bar will be equal to 0, because these supports are not moving with respect to each other. So total length before and total length after will be same. So change in length, total change in length will be 0. So total change in length will be equal to change in length of this bar plus change in length of this bar, and that will be equal to 0. So I'll be getting another equation by compatibility condition that delta will be equal to delta 1 plus delta 2, and that will be equal to 0. Now what will be the value of delta 1? Now the total elongation will be because of two factors. One factor is temperature, and other factor is the stresses that are generated in the bars. So because of temperature, temperature is reducing. So when temperature is reducing, because of temperature, the length will be getting reduced. Okay, so it will come with negative sign. And because of stresses are tensile in nature. So because of stresses, tensile stresses, there is a tendency of increase in length. So in both the bars, because of stresses, we will be having tendency of increase in length, and because of temperature drop, we'll be having tendency of reduction in length. Okay, so if sigma 1 is the tensile stress in this bar, change in length will be equal to how much? Change in length delta 1. Delta 1 will be equal to how much? Delta 1 will be equal to sigma 1 upon E will be strain into L1, that will be change in length. So sigma 1 upon E, this is strain, and multiplied by length, that will be L1, and this will be positive because tensile stress. Now because of temperature drop, the change in length will be L alpha T. L alpha T, that means L1 alpha T. Okay, so this is delta 1 plus delta 2 will be sigma 2 by E into L2 minus L2 alpha T. Okay, sigma 1, what is the value of sigma 1? Sigma 1, 9 by 16, sigma 2, 9 by 16, sigma 2 into L1. What is the value of L1? L1, this length is 200 mm. So 200 plus, sorry, this will be minus 200 into alpha. What is the value of alpha? Okay, just a minute. Now what I can do, I have to calculate sigma 1, sigma 2. Okay, let us put sigma 1 and sigma 2 on one side and L1 terms on the other side. Okay, so sigma 1 L1 plus sigma 2 L2 whole upon E will be equal to L1 plus L2 alpha T, that will be on other side. Okay, so that means sigma 1 L1 plus sigma 2 L2 will be equal to total length L into alpha T into E. Okay, this is the final equation that we are getting, and from here if we keep all the terms, we'll be getting the final answer. So sigma 1, 9 by 16 sigma 2, 9 by 16 sigma 2 into L1. What is the length L1? 200 mm plus sigma 2 into L2 is 100 mm length, that will be equal to total length is 300 mm into alpha is 12.5 into 10 to the power minus 6. 12.5 into 10 to the power minus 6 into temperature change is 30 degrees Celsius into Young's modulus is 200 giganewton per meter square. Now answer, we have to answer, options are given in meganewton per meter square. So we have to convert this 200 giganewton per meter square into meganewton per meter square, and that will be 200 into 10 to the power 3. So 200 into 10 to the power 3. Okay, now if I solve this, I will be getting 9 by 16 into 200 plus 100. 9 by 16 into 200 plus 100, I am getting 212.5. So 212.5 sigma 2 will be equal to, let us calculate this. So how many zeros are there? 2 zeros, 3 zeros, 3, 4, 5, 6, 7, 8. 8 zeros are here, and 10 to the power minus 6 zeros are gone. So we will be left with 2 zeros, then 3 into 12.5 into 3 into 2. So 3 into 12.5. 12.5 into 2 will be 25. 25 into 9. 25 into 9, 225. So 22500. Okay, so sigma 2 will be equal to 22500 divided by 212.5, that will be 105.88 105.88 mega Newton per meter square. This is the correct answer, and options are not matching exactly. Option, we have to choose nearest option. So nearest option is option D, 100 mega Newton per meter square. So correct answer will be option D. Clear? Let's move on to the next question. Next question, a rigid beam CBDA. So rigid beam CBDA is hinged at A. So it is hinged at A and supported by two springs at C and B. So here is one spring, here is another spring C and B with a vertical load P at point D as shown in the given figure. The ratio of stiffness K2 upon K1 of springs B and C is 2. So K1 upon K2 is given as 2. Ratio of forces in spring at C to that at B, that we have to calculate. Okay, so now because of this load, what will happen? This bar is rigid bar. Okay, so this bar will deflect something like this. Okay, because of this load there is downward force, and this downward force will have tendency to deflect this bar in vertical direction downward, vertically downward direction. Okay, like this, like this. Okay, now here in this bar, let us say force developed is PB, and here the force developed is PC. Okay, so what is the ratio of forces in springs at C to that at B? So PC upon PB, that we have to calculate. So PC upon PB. Now force in spring, force will be equal to K delta. That we know. Okay, so P equal to K delta. So PC upon PB is equal to KC upon KB into delta C upon delta B. This will be the ratio. Now we have to find out the ratio of KC upon KB. Good evening, Saurabh. So KC upon K2, KC upon KB, K1 upon K2, that ratio is given as 2. Already given in the question, this is 2. And delta C upon delta B. Now this we can find out by using similar triangles. Okay, so this is delta C, and this is delta B. So delta C upon delta B from similar triangles will be getting 3 upon 2. So that will be equal to 3 upon 2. So delta C upon delta B is 3 upon 2. Let us multiply 3 upon 2. We'll be getting PC upon PB will be equal to 3. Okay, so correct answer is option 3. Option. Spring C to spring B, delta C upon delta B, 3 by 2, right? That is 3 by 2, and this is given as 2. Stiffness K2 upon K1, sorry, K2 upon K1 is given as 2. Okay, not K1 upon K2, K2 upon K1 is 2. So K2 upon K1 is 2. K2 upon K1 is 2. That means this will be 1 by 2. This will be 1 by 2. So it will be 3 by 4. Correct answer will be option A. Option A, 3 by 4 is the correct answer. Okay. Let's move on to next question. Is this clear? Any doubt in this question? Let's move on to next question. So next question, a bar of uniform section is subjected to axial tensile loads such that the normal strain in axial direction is 1.25 mm. So this is the bar. Okay, it is subjected to axial tensile loads. Axial loads are acting on this bar like this. So normal strain epsilon x will be equal to 1.25 mm per meter. Per meter, that means per 1000 mm. Okay, so this will be the normal strain in axial direction. If the Poisson's ratio of the material of the bar is 0.3, the volumetric strain would be. So volumetric strain, we have to calculate volumetric strain. So volumetric strain will be equal to epsilon x plus epsilon y plus epsilon z. Now, just tell me, because of this axial loading, there will be only axial stresses or there will be transverse, because of this axial loading, will there be only axial strains or there will be transverse strain, lateral strains also. Because of this axial loading, there will be only axial strain or there will be strain in other directions also. Strain will come in other directions also. Okay, so because of this axial stress, strains will be developed in 3 dimensions. Okay, so we have to calculate epsilon y also and epsilon z also. Okay, so epsilon y, what will be the value of epsilon y? Epsilon y will be equal to minus mu epsilon x and epsilon z will be equal to minus mu epsilon x. Okay, so we can put these values here. So epsilon x minus mu epsilon x minus mu epsilon x. Okay, so epsilon x into 1 minus 2 mu, this will be the volumetric strain. This will be the volumetric strain. Yes, Poisson's ratio effect will be there. So volumetric strain can be calculated like this. Now if I put all the values, so volumetric strain will be equal to epsilon x. What is the epsilon x? 1.25 into 10 to the power minus 3. 1.25 into 10 to the power minus 3, and here 1 minus 2 mu. So mu value is 0.3. So 1 minus 2 into 0.3, that means 1 minus 0.6, 1 minus 0.6, that means 0.4, 0.4 into 1.25. So 1.25 into 0.4, 10 to the power minus 4 into 4, 1.25, 2.5, 2.5 into 2, 5. So we'll be getting 5 into 10 to the power minus 4. Yes, 5 into 10 to the power minus 4. Correct answer will be option D. Option D is the correct answer. Clear? Okay, let's move on to next question. Next question is match the following. So match list 1. In list 1 we are given elastic constants, and list 2 is the definition of those elastic constants. Okay, so Young's modulus. What will be the Young's modulus? Young's modulus, stress to strain within elastic limit. Okay, so Young's modulus will be 2. Poisson's ratio, lateral strain to linear strain within elastic limit, 1. Bulk modulus, direct stress to corresponding volumetric strain. Bulk modulus, direct stress to corresponding volumetric strain. So bulk modulus will be 4. Rigidity modulus, shear stress to shear strain. So that will be 3. So 2, 1, 4, 3 will be the sequence. Yes, 2, 1, 4, 3. So let us see. 2, 1, 4, 3. Option B is the correct answer. Option B is the correct answer, right? Easy question. Next question. This is a little bit tricky question. A square plate A by A rigidly held at the 3 edges is free to move along the 4th edge. Okay, so we are having a square plate. So square plate is something like this. Okay, so this is restricted at 3 edges. At this edge it is restricted to move. At this edge also it is restricted. Okay, effectively held in position. At this edge also it is effectively held in position. So it is like this. Okay, but it is free to move along the 4th edge. It is free to move along the 4th edge. So we can slide inside and outside in this. Okay, there is just say there is some slot. Okay, so it perfectly fits in that slot. Okay, now if I increase the temperature, what will happen? The material wants to increase in all the directions. Material wants to increase its length in all the directions, but it is not allowed to increase in this direction. The length will increase only in this direction, only in x direction. Let us say this is x direction, this is x direction, and this is y direction. So only in x direction it is free to move. Okay, so length will increase only in x direction. Now if the temperature of the plate is raised by temperature T, then the free expansion at the 4th edge will be. So we have to find out the free expansion at the 4th edge. Now you tell me what will be the free expansion. Okay, the edge distance, the edges, both the edges, this is square plate, no? So both the edges are of side A and A. Okay, all the edges are of same side. Okay, so length will be A and A. Now the increase in length here will be because of what? Because of two things. What two things? First, temperature rise. Okay, when temperature is rising, obviously this length will increase. Yes or no? When temperature will rise, this length will increase. So because of temperature rise, we will calculate. But there is one other thing. When temperature is rising, this plate is trying to increase its length in this direction also. When temperature is rising, it is wanting to increase the length in this direction also. But here, these are supports. Okay, so this will not allow any increase in length. So when the length is not increasing, it is providing a compressive force. When compressive force is applied like this, so it will have an effect of increasing length in this direction because of Poisson's effect. Okay, so because of Poisson's effect also, so there are two things playing. Two things are contributing in the increase in length in this direction. First, temperature rise, and second, compression due to thermal stresses in lateral direction. So in this direction there is compression, because of that there will be increase in length. Okay, so because of these two things we have to calculate. Okay, so total increase in length in x direction will be equal to increase in length in x direction due to temperature change plus increase in length in x direction due to lateral stress. Okay, so because of temperature rise, we are having the formula L alpha T. Okay, L alpha T. In place of L, I'll write A. So A alpha T. This is the length, this is the change in length due to temperature alone. Okay, next, plus this will be strain in x direction minus mu stress in y direction by E. Like this we write. Strain in x direction will be equal to minus mu into stress in y direction by E. Okay, now this is strain. We have to multiply with length also. So change in length in x direction will be equal to minus mu sigma y into length by E. Okay, so in place of, so we have to write minus mu sigma y. What is the stress? What is the stress developed? Stress will be alpha TE. Alpha TE will be the stress, and that stress will be tensile or compressive. That stress will be tensile or compressive. It will be compressive stress. So we'll put a minus sign here. So minus alpha TE, that is the stress. Okay, so minus mu sigma y, we have written length. What is the length here? This dimension is also A. Okay, length divided by E. So E and E will cancel out. E and E will cancel out. Okay, minus and minus will cancel out. What we will be getting finally? Finally we will be getting A alpha T plus mu alpha T A, mu A alpha T. Okay, so we can take A alpha T common, and 1 plus mu will be in bracket. Okay, so this will be the answer. A alpha T 1 plus mu. Correct answer will be option B. Are you able to understand? Are you able to understand? Did you understood this? So it will be 1 plus mu. Why plus will come? Because the both factors will be playing. Okay, if this stress was tensile, then here minus sign would come. It will have tendency to reduce the length. But here compressive stress is coming, so that will have the tendency to increase the length in this direction. So that's why we'll be getting plus. Okay, next question. For linear elastic isotropic material, the number of independent elastic constants is. Okay, this is very easy question. So total number of elastic constants, you know, E, G, K, mu. 4 elastic constants are there, but independent elastic constants are 2 only. So correct answer will be option B. 2 are the independent elastic constants. Okay, next question. Creep is the gradual increase of plastic strain with the time at constant load. Option A is correct. Okay, first option itself is correct. So correct answer will be option A. Yes. Match list 1 with list 2. Okay, list 1 are the properties. Properties are what? Yield point, proportional limit, rupture strength, ultimate strength. And list 2 stress points labeled 1, 2, 3, 4 like this. Okay, in the stress strain figure, and select the correct answer. Okay, so correct answer means I think we have to find out. Okay, yield point. Which is the yield point? Can you tell me? 1, 2, 3, 4. Which one will be the yield point? Which one will be the proportional limit? Rupture strength and ultimate strength. First we will find, at first we will find proportional limit. Okay, so proportional limit will come first. So proportional limit, this is 4. Okay, after that we will get yield point. After proportional limit we will get yield point, so it will be 3. Rupture strength at the point which the material will rupture, okay, will break apart, so that will be 1. Rupture strength is represented by 1, and ultimate strength, the highest strength, it should be somewhere here, but anyways, okay, so ultimate strength is given by 0.2. So 3, 4, 1, 2, this will be the correct answer. 3, 4, 3, 4, 1, 2 should be the correct answer. Let me check. 3, 4. First option is 3, 4, 1, 2. Some typing mistake is there. So this will be 3, 4, 1, 2. Okay, so correct answer is option A. Option A is the correct answer. Okay, yes, 3, 4, 1, 2 is the correct answer. Next, assertion. Okay, assertion. The strain and stress system for a bar of length L subjected to an axial pull will be same whether both ends of the bar are free or one end is fixed and the other is free. Okay, so the stress and strain system for a bar of length L. So this is the bar. This is the bar of length L. Okay, so stress strain system for this bar will be same whether both ends of the bar are free or one end is fixed and other is free. Okay, so there are two scenarios. First scenario, that one end is fixed and other is free, and second scenario, both ends of the bar are free. Okay, in this scenario both ends are free. Now if we apply load here like this, P load, okay, P load I'll apply. What is the force? What is the force in this bar? In this bar entire force will be P, axial force tensile, right? Axial tensile force will be there. And in this bar, if I apply force like this, P and P, what will be the force in this entire bar? That will be again tensile force P. So these two are same, equivalent or not? Same stress and strain system will be generated or not? The stress and strain system for a bar of length L subjected to an axial pull. This is also axial pull. The pull is applied in axial direction, and in this also pull is applied in axial direction. So in both the bars we are applying a pull in axial direction. Okay, and this pull, the condition in first case is one end is fixed and other is free, and in second case both the ends are free. Okay, so does this change anything? No, they are equivalent. Okay, so stress strain system will be same. This is correct. Okay, stress strain system will be correct. Okay, reason: rigid body displacements have no effect on the elastic deformations. This also is correct. Rigid body displacement have no effect on the elastic deformation, but here rigid body displacement is not taking place. Okay, so in this, do we talk about rigid body displacement anytime? No. Okay, pull is applied. That is understood, that pull is applied, equal and opposite forces are acting, the body is in equilibrium, so there will be no rigid body displacements. Okay, so if I talk about this statement individually, this statement is correct, but it is not explaining this. This is not the explanation, right? Correct. So this is also true, this is also true, but it is not the correct explanation. So correct answer will be option B. Option B is the correct answer. Clear? Any problem? Let's move on to the next question. Next question: the bulk modulus of elasticity of a material is twice its modulus of rigidity. That means K is equal to 2G. This is given. The Poisson's ratio of the material is. Now this, for this you must know all the 4 equations of elastic relationship between elastic constants. Okay, even if you don't know all the 4 equations, you must know at least first 2 equations. Okay, so from first 2 equations we can also calculate, but if we know the other equations as well, then it will be easier. Okay, so mu is equal to 3k minus 2g upon 6k plus 2g. This is the relationship between mu, k and g. Now k is 2g, so 3k into 2g, that means it will be 6g minus 2g divided by 6k, that means 12g plus 2g. I'll be getting 4g divided by 14g. I'll be getting 2 by 7. So mu will be equal to 2 by 7. Otherwise, there is another method. E is equal to 2g 1 plus mu, and E is equal to 3k 1 minus 2 mu. Okay, if you remember these 2 equations, then you can equate these two, and then also you can calculate, so same answer will be coming. Okay, but if you remember this, then you will be finding in less amount of time. Okay, clear? So correct answer is option B. Next question, creep of a material is a property indicated by, creep of a material is property indicated by time dependent strain of the material. Okay, so it is time dependent strain. Correct answer will be option A. Next, resilience. What is resilience? Resilience is recoverable strain energy. So whatever strain energy that we are storing in the material, if it can be recovered, that is resilience. Okay, so strain energy within elastic limit, it can be recovered. If we apply the strain energy, if we put the forces that strain energy increases beyond elastic limit, then that part cannot be recovered, right? So correct answer is option B. Very good. Next question, assertion. Normal stress of one nature may be compressive or tensile if I am applying normal stress of one nature, okay, on this material. Okay, so normal stress of one nature, compressive or tensile, acting along one of the 3 orthogonal axes. So if normal stress of one nature, let us say I am applying tensile on one of the 3 axes, orthogonal axis of a member, will produce strains of the same nature in its direction. So if I have applied tensile stress, the strain will be tensile, yes or no? If I apply compressive stress, then strain will also be compressive. Okay, the length will be reducing along the direction of application of stress. So if I have applied stress in this direction, so in this direction I will be getting strain that is of same nature of the stress. So stress and strain will be having same nature, yes, and strains of opposite nature along the other 2 directions. So along other 2 directions, the strains will be of opposite nature. So I have applied stress, tensile stress here, so I will be getting tensile strain like this. So here I will be getting compressive strain, here also I will be getting compressive strain. Okay, so this statement is correct, assertion is correct, this is true. Reason, sum of the strains along the 3 orthogonal axes equals volumetric strain. This is individually true, but this is not explaining. Correct explanation would be Poisson's ratio, right? Poisson's ratio, right? But this is explaining that volumetric strain will be equal to epsilon x plus epsilon y plus epsilon z. So individually this is correct, this is true, but it is not explaining this. So correct statement will be, correct answer will be option B. Option B will be the correct answer. Clear? Right? Next question. A rigid bar AC is supported by 3 rods of same material and of equal diameter. Okay, so these 3, this is rigid bar AC. This is supported by 3 rods. These are the 3 rods. Okay, these are of same material. So same material means Young's modulus is same. So Young's modulus E, 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 same for all. Okay, equal diameter. So area of cross section is also same. A, A, A. This is also same. Okay, the bar AC is initially horizontal, so this is horizontal. Okay, lengths are given, this length is L1, this length is L1, and this length is 2L1. Okay, so bar AC is initially horizontal. Force P is applied such that the bar AC continues to remain horizontal. Okay, so force P is applied, then there will be some deformation, there will be some deflection in this bar, but after deflection also this will remain horizontal. What does this imply? This implies that change in length of this bar, change in length of this rod, okay, change in length of this rod and change in length of this rod, change in length of all the rods is same. They are increasing by same amount. Okay, so change in length is same. Forces in each of the shorter bars and in the longer bar are respectively. Okay, so let us say force in shorter bar is represented by PS. Force in longer bar is represented by PL. Force in shorter bar is represented by PS. In both the shorter bars, force will be same, and in longer bar, force will be different. Okay, so one equilibrium equation we can right away formulate, that will be 2PS plus PL is equal to external force P. Okay, this is the first equation. This is coming from equilibrium equation. Now, if I apply compatibility condition, so compatibility condition says that deflection in all the three bars is same. Deflection in all the three bars is same. Okay, so this deflection is equal to this deflection. So deflection in all the three bars is same, delta, delta, delta. Okay, so delta of shorter bar will be equal to delta of longer bar. So delta of shorter bar will be equal to PS LS upon AS ES, and change in length of longer bar will be equal to PL LL PL upon AE AL EL. Okay, now I know that area of shorter bar and area of longer bar both are same. Young's modulus of shorter bar, Young's modulus of longer bar both are same. Okay, so they can be cancelled out from both the sides. Okay, so the ratio of force in shorter bar and longer bar will be equal to the ratio of their length. Okay, so force in shorter bar divided by force in longer bar will be equal to length of longer bar divided by length of shorter bar. What is the length of longer bar? 2L1, and length of shorter bar is L1. So that will be equal to 2L1 upon L1. L1 and L1 will cancel out. So force in shorter bar is equal to 2 times the force in longer bar. Force in shorter bar will be equal to 2 times the force in longer bar. Now if I put in this equation 2PS plus PL is equal to P. So this is equation 2. Okay, so PS 2 into 2PL plus PL is equal to P. So 5PL is equal to P. That means force in longer bar is equal to 0.2 P. And force in shorter bar will be equal to 0.4. Okay, so force in shorter bar, force in longer bar, 0.4 P, 0.2 P. Correct answer will be option A. Option A is the correct answer. Are you able to understand? Any doubt? Is it clear? Okay, so let's move on to the next question. Okay, so next question, a member having length L, cross-sectional area A and modulus of elasticity E is subjected to an axial load W. Okay, yes, a member having length L, length is L, cross-sectional area A and modulus of elasticity E subjected to axial load W. Okay, the strain energy stored in the material. So strain energy stored, that means we are talking about total strain energy stored. So total strain energy stored will be equal to how much? First of all, we'll represent this total strain energy by capital U, and that will be equal to half P delta. Half, what is the force P? P is given by W, and delta will be equal to PL upon AE. That means we'll do WL upon AE. Okay, so we'll be getting W square L upon 2AE. So total strain energy stored will be W square L upon 2AE. W square L upon 2AE. Correct answer will be option C. Clear? Next question. Elastic limit is the point up to which stress is proportional to strain. That will be proportional limit. Right? Proportional limit. At which elongation takes place without application of additional load, that will be yield point. Up to which if the load is removed, up to which if the load is removed, original volume and shape are regained. Yes, that is elastic limit. This is elastic limit at which the toughness is maximum. There is no such point that toughness is maximum. At that point, toughness is maximum. Okay. So correct answer will be option C. C is the correct answer. Clear? Let's move on to next question. Match list 1 with list 2 and select the correct answer using the codes given below the list. Okay. So isotropic material. Isotropic material means identical properties in all the directions. Okay. So 3. Homogeneous material, similar properties throughout the volume. 4. Viscoelastic material, time dependent stress strain relation. 1. Brittle material, no plastic zone. 2. Okay. So 3, 4, 1, 2 will be the correct answer. 3, 4, 1, 2. Okay. Correct answer is option C. Option C is the correct answer. Okay. Next question, ductile material, correct answer is option C. Very good, Saurabh. Okay. Next, as per the elastic theory of design, the factor of safety is the ratio of. So when we are talking about elastic theory of design, although this should come in design, but let us still discuss it. As per elastic theory of design, in the elastic theory of design, we keep the stresses in elastic limit. Okay. So within elastic limit, let us say we are considering yield stress sigma y as the maximum stress. Okay. So we will not allow, actually we will not allow going beyond sigma y. If it reaches sigma y, we will consider that failure has happened. But in addition to that, we will apply some factor of safety. So if we include the factor of safety, whatever is the factor of safety, will reduce the permissible stress by that ratio, by that factor of safety, and the actual stresses that should come into the material, that will be lower than these yield stress. Okay. And these are called as working stress. So what will be the factor of safety? Factor of safety will be the ratio of yield stress sigma y upon sigma w. Okay. So that will be yield stress divided by working stress. Working stress. Clear? So yield stress to working stress. Correct answer is option B. Okay. So correspond as per elastic theory of design, we will be getting option B as answer. Okay. Yes, this is RCC question. Next question. Principal strains at a point are given. Okay, so this is the principal stress. First principal stress 800 into 10 to the power minus 6 centimeter per centimeter. Second principal strain 400 into 10 to the power minus 6 centimeter per centimeter. And third principal strain, there are 3 mutually perpendicular directions, so there will be 3 principal strains only. Okay, this minus 1200 into 10 to the power minus 6 centimeter per centimeter. Volumetric strain will be, so we know volumetric strain epsilon V will be equal to epsilon X plus epsilon Y plus epsilon Z. Okay, what will be epsilon X? It will be plus 800 into 10 to the power minus 6 plus epsilon Y will be 400 into 10 to the power minus 6 and minus 1200 into 10 to the power minus 6. Okay, so 800 plus 400, 1200, 1200 minus 1200, 0. Okay, so correct answer will be option D. Volumetric strain will be 0. Next question. The stress is in concrete in reinforced concrete element under sustained load due to creep. Stresses in concrete in RCC element under sustained load due to creep. So stresses, what will happen to the stresses under sustained loading? So basically we teach this phenomena separately. This is basically they are asking relaxation. But relaxation and creep, basic concept, underlying concept is same in relaxation and creep. Both are having same underlying concept. Okay, so here the stresses in reinforced concrete element under sustained load due to creep, the stresses will decrease. Okay, that will be called as creep relaxation. Okay, so increase with time? No, decrease with time. Stresses will be decreasing with time, and this phenomena is more specifically called as creep relaxation, but we can also say creep because of creep it is happening. Okay, more specifically creep relaxation, right? Next question. A brass bar of solid section is encased in a steel tube. Okay, so this is the brass bar, solid section, it is encased. So outer casing is of steel and inner is brass. Okay, as shown in the diagram. Okay, so here is the fixed support and here they are attached together by some rigid element. Okay, such that if if they elongate, they will elongate by same amount, and if they compress, they will be compressing by same amount. Okay, so change in length will be same for both steel and brass. Okay, they are fixed like this. Okay, encased like this. Then the coefficient of expansion of steel is this much and the coefficient of expansion of brass is this much. Okay, so coefficient of expansion of brass is higher than that of steel. Please explain it. Which question? Creep one or this one? Please specify, because there is some time lag when your comment comes. Previous? This one? See, creep is the phenomenon by which strain keeps on increasing at constant stress. Okay, creep relaxation is a phenomenon. This is basically dependent on creep only, but it is manifesting in another way. Here the strain is constant. Here the strain is constant. So at constant strain, stress keeps on reducing. Okay, so this phenomenon is creep relaxation. So if I keep stress constant and strain keeps on increasing at constant stress with changing time, with increasing time, so time is increasing 10 years, 20 years, 30 years, but stress is constant. So what will happen? My strain will keep on increasing and this will be plastic strain. Okay, but if I make an arrangement differently, okay, same material I am taking, but some different kind of arrangement I have made such that my strain is constant, I am not changing the strain, so automatically what will happen? The stress will start reducing in that case. Okay, so we have termed these as separate phenomena, but the internal mechanism what will be happening, that will be same. Okay, we don't need to go into the internals of the structure, but from outside what we will see is that if I have made an arrangement that I am keeping the stress constant, so my strain will keep on increasing with time. But if I have made an arrangement such that my strain is constant, then I will see that my stresses are reducing with time. Okay, so that is creep relaxation. So in concrete what will happen? That creep relaxation will be taking place. Okay, now here in this question, brass of solid section is encased in steel tube. Okay, and coefficient of thermal expansion of steel is less than that of brass. Okay, so coefficient of thermal expansion of steel is less than that of brass. Now if I increase the temperature, okay, the composite bar is heated through 60 degrees Celsius. So if I increase the temperature is increasing. Which one will expand more? So delta L, change in length, will be equal to L alpha T. Okay, so temperature, both bars are heated by same temperature, length of both the bars is same. Okay, so change in length will depend on alpha only. Okay, so whichever material is having higher coefficient of thermal expansion, that will try to expand more. Okay, that will experience more expansion. So if that will experience more expansion, that will try to expand more. Okay, but the other material will not try to expand that much. So what will happen? Change in length should be same, will be same. Okay, in that case, because their ends are rigidly attached to each other. Okay, with one another they are rigidly attached. Okay, so if brass wants to expand more, steel does not want to expand more, what will happen? Brass wants to go expand up to this limit, but steel wants to expand up to this limit only. Okay, so what will happen? They will expand somewhere here. Okay, so brass will have to experience some compression because of steel. Okay, because of steel, the brass has to come to this location, but in turn the steel has to increase its length. Okay, so brass will be experiencing compression. There will be compression in brass and there is tension in steel. Okay, so stress in the brass will be tensile. Wrong. Stress in the steel will be tensile. Yes. Stress in the steel will be compressive. No. Stress in the brass will be compressive. Yes. Okay, so 2 and 4 will be the correct. 2 and 4, option C is the correct answer. Is it clear? Okay, so 2 and 4 both are correct. Stress in steel will be tensile, yes, and stress in brass will be compressive. Clear? Okay. Next question. A mild steel bar of square cross section 40 mm into 40 mm. So cross section is 40 mm into 40 mm, is 400 mm long. So this is the length. It is subjected to a longitudinal tensile stress. Okay, so this is the longitudinal tensile stress, let us say sigma x, and lateral compressive stress, let us say this is sigma y. Lateral compressive stress. See, this is tensile stress, so I'll put positive here. This is compressive stress, I'll put negative here, minus 200 Newton per mm square in perpendicular direction. Okay. So in only one perpendicular direction stress are there. Okay. In another perpendicular direction stress is not there. Okay. So sigma z is 0. Now Young's modulus E is equal to 2 into 10 to the power 5. Poisson's ratio is 0.3. What is the approximate elongation of the bar in the longitudinal direction? Approximate elongation. Okay. So delta L will be equal to how much? Epsilon x in the longitudinal direction, epsilon x into length in x direction. Okay. So change in length in x direction will be equal to strain in x direction into length. Okay. Now how to calculate strain in x direction? Strain in x direction will be equal to sigma x upon E minus mu sigma y upon E minus mu sigma z upon E. Okay. So what will be the value of sigma x? Sigma x is 440 Newton per mm square. 440 Newton per mm square upon Young's modulus 2 into 10 to the power 5. Okay, minus mu is 0.3 into sigma y is minus 200 upon 2 into 10 to the power 5, and sigma z is 0. Okay, so we are getting 2 into 10 to the power 5 here. 440 plus 0.3 into 200, so 60. 440 plus 60, that means 500 divided by 2 into 10 to the power 5. Okay, 500 divided by 2 into 10 to the power 5. This is the strain in x direction. Now I have to calculate change in length in x direction. So change in length in x direction, delta L in x direction will be equal to strain, that is 500 divided by 2 into 10 to the power 5 into what is the length in x direction? Length in x direction is 400 mm. So this is 400 mm. Okay. So (440) divided by minus 0.3 into 200. 2 3s are 6, 60. Okay. So it will be positive. 440 plus 60. 500 divided by 2. So 250. Or we can write it as 1 by, let us multiply 2 and 2. Okay, so at top we are getting 1000 divided by 4 into 10 to the power 5 into 400. Okay, so at top we are getting 1 2 3 4 5 5 zeros and 5 zeros, 4 and 4 cancel out, we will be left with 1 mm. Okay, so change in length in x direction will be equal to 1 mm. 1 mm is the correct answer, so option D is the correct answer. Clear? Option D is the correct answer. Let's move on to the next question. If the Young's modulus E is equal to the bulk modulus K, then what is the value of Poisson's ratio? Okay, so Poisson's ratio we have to calculate. So E is equal to 3k 1 minus 2 mu. Okay, so we have to calculate Poisson's ratio. E and k are equal, so E is equal to 3e 1 minus 2 mu. So E and E will get cancelled out. Okay, so what we'll be getting, this will be 1 by 3 is equal to 1 minus 2 mu. So 2 mu will be equal to 1 minus 1 by 3. That means it will be 2 by 3. So mu is equal to 1 by 3. Mu will be equal to 1 by 3. Correct answer is option C. Option C. Yes? Okay. Clear. Very good. Next question. If G is the modulus of rigidity, so you can see relationship between elastic constant. So many questions are asked based on this. So G is the modulus of rigidity, E is the modulus of elasticity, and mu the Poisson's ratio for a material. Then what is the expression for G? Okay. So G, E is equal to 2G1 plus mu, that we know. So G will be equal to E upon 2 1 plus mu. So E upon some mistake in options. Let me check. Three E upon 2 1 plus 2 mu, 5E upon 1 plus mu, E upon 2. Oh, correct. Correct answer will be option C. No mistake in options. Correct answer is option C. Right? So G is equal to E upon 2 1 plus 2 mu. No, 1 plus mu. That's why. It will be 1 plus mu. Mistaken option. Yes. Correct answer will be this. Typing error is there, but anyways, no problem. Okay. Now next. And here also in option D also there is typing error. In option D, this should be E upon. So these are the correct options. Anyways, no problem. Next question. 3 wires of steel 1, 2 and 3 each having area A. So area of this steel wire is A. All are having area A. Support a load W as shown in the figure below. What is the ratio between collapse load and the load corresponding to the yielding of one of the wires? Okay, collapse load and load corresponding to yielding of one of the wires. Now can you tell me which wire will yield first? Which wire will yield first? Area is same, material is same. Okay, steel wires. All the wires are made of steel, so steel wires. Okay, area is same, cross-sectional area is same, material is same, length are different. Okay, so load is applied. Now we are slowly we are increasing the load. Slowly and slowly we are increasing the load, increasing the load, increasing the load, increasing the load. Okay, there will be a point where one of the wires will lead first. Okay, one or maybe two wires. If this wire is yielding first, then both will yield at the same time, and if this wire is yielding, then this will yield first. Okay, so when any of the wire is yielding, so when first wire yields, okay, at that time what is the load here? Okay, then we'll further keep on increasing the load, increasing the load, increasing the load, and there will be a time when entire system will collapse. There will be a time when entire system will collapse. So corresponding to that load, okay, we'll be getting some value of W. Okay, corresponding to that we'll be getting some value. So what is the ratio between these two? Okay, so ratio we have to find out. Okay, so first of all, stress in wire 1 and stress in wire 2, we have to calculate the ratio of stresses of wires 1 and 2. Okay, now one thing we know, that deflection of both the wires is same. Okay, deflection of both the wires is same. Both the wires will deflect by same amount. Okay, so this wire will also deflect by same amount, this wire will also deflect by same amount, this wire will also deflect by same amount. Okay, So this is 1 and 2. So deflection of wire 1 will be equal to deflection of wire 2, and deflection of wire 1 will be deflection. Okay, if we want to calculate in terms of stress, okay, so stress sigma 1 upon Young's modulus into L1, that will be equal to sigma 2 L2 upon E. Yes or no? This will be strain. Okay, strain sigma 1 upon E will be strain into length. This will be deflection. Sigma 2 upon E will be strain in this wire into length L2. Okay, now E and E both are same, they will cancel out. Okay, sigma 1 upon sigma 2 will be equal to how much? L2 upon L1. L2 upon L1. What is the length of 2? Half. It will be L by 2. L by 2 divided by length. This is L. So sigma 1 upon sigma 2 is equal to half. What does this mean? What does this mean? That at the same elongation, and when we are applying the load W, this wire will have half the load or half the stress. It will carry half the stress as compared to this wire. Yes or no? Does this mean this or anything else? And when stresses are, stress ratio is this, then load ratio will also be same, because load will be what? If we multiply area is also same. So P1 upon P2 is also same, na? So this will carry half the load as compared to this wire. This will be carrying more load. Okay. Now this is within elastic limit. When we are within elastic limit, this is the ratio. Okay. Now which wire will yield first? The wire that will be carrying more load. Okay, so this wire is carrying more load, this wire will yield first. And when this wire will yield, let us say at the time of yielding, this wire is carrying yield load Py. At the time of yielding, let us say this wire is carrying load Py, and this wire will be carrying load Py by 2. Yes or no? Half the load as compared to this, and this wire will also be carrying load Py by 2. Okay, so what will be the value of W? Okay, so load W corresponding to yielding of first wire. So when first wire is yielding, what will be the load W? So W will be equal to Py by 2 plus Py plus Py by 2. So that will be equal to 2 Py. W will be equal to 2 Py. W will be equal to 2 Py. Okay, so this W load corresponding to yielding of first wire. Now we have to calculate load, total load W corresponding to collapse. When will collapse happen? When will collapse happen? Now this wire has yielded. When this wire has yielded, I am still increasing this load. What will happen to the load here? What will happen to the load here? See, to understand this, you have to consider the stress strain curve of steel. So stress strain curve, idealized stress strain curve of steel is like this. We idealize the stress strain curve like this. This is the stress strain curve of steel. Okay. Now when the first wire has yielded, corresponding to this, the stress is sigma y. Stress is sigma y, and load will be sigma y into area. Py is sigma y into area. Okay, so Py will be sigma y into area. Now after yielding, if we keep on increasing the strain, there is no increase in stress. Okay, we will not consider any increase in stress. So sigma y will remain up till fracture. Okay, up till fracture, the consideration will be that sigma y is sigma y. It is not changing. Okay, so load will be not changing. Even if we are increasing the W, okay, so the force in these two wires is changing. This is increasing, but force in this wire has remained. Now it will remain constant. Okay. Now, if we keep on increasing the W, what is the maximum force that this wire can take? This wire can take maximum force of Py. This wire can take maximum force of Py, and this wire can take a maximum force of Py. Now corresponding to collapse load, this wire will be taking force Py, Py, Py. All the three wires will be yielded. Okay, so when all the three wires have yielded, all the three wires will be having this stress strain curve now, and now collapse load is corresponding to yielding of all the three wires. Okay, so collapse load, okay, W corresponding to collapse load, that means yielding of all the three wires, yielding of all the three wires. Okay, so W will be E collapse, and this is yielding of first wire, so that will be equal to Py plus Py plus Py, that will be equal to 3 Py. So corresponding to collapse load, W will be this much. Okay, so what is the ratio between the collapse load? Collapse load will be 3 Py, collapse load divided by yielding of first wire, so 3 Py divided by 2 Py, so we'll be getting ratio 3/2. Are you able to understand it? Got it? Ratio is 3/2. 3:2 is the ratio. Correct answer is option B. Done? Are you able to understand? Got it? Okay, so let's move on to the next question. A bar of 40 mm diameter and 400 mm length is subjected to an axial load of 100 kilonewton. Okay, so we are having a bar, diameter is 40 mm, length is 400 mm, okay, subjected to load of 100 kilonewton. 100 kilonewton. It elongates by 0.15 mm. So delta L is equal to 0.15 mm, and the diameter decreases by, decrease in diameter, that will be minus 0.005 mm. What is the Poisson's ratio of the material of the bar? So Poisson's ratio will be equal to how much? Poisson's ratio is lateral strain divided by longitudinal strain. Okay, so Poisson's ratio, lateral strain will be 0.005 divided by, means lateral strain, change in diameter divided by original diameter. So change in diameter is this 0.005 divided by original diameter is 40 mm. So 40 mm, let us write first formula. Let me write change in diameter divided by original diameter into it will be divided by change in length divided by original length. So original length will go up. Okay, so original length divided by change in length. So what is the change in diameter? Change in diameter is given as 0.005 mm. I am not putting minus sign because when I take mod, it will automatically become positive. Okay, so no need to take minus sign. So 0.005 divided by original diameter is 40 mm into what is the length? Length was 400 mm. So original length was 400 mm. Change in length is 0.15. Okay, so if I cancel out these two, I will be getting 10 here. Okay, so it will be 0.05 divided by 0.15, that will be 5/15, that will be 1/3. So mu is equal to 1/3. Clear? So 0.33 will be the correct answer. Yes, option C is the correct answer. Very good. Next question. If P1 and P2 are principal stress at a point in a strained material with Young's modulus E and Poisson's ratio 1/m, let us first put Poisson's ratio mu, and then later on we will replace Poisson's ratio 1/m. Okay, so initially let us put mu only. So if P1 and P2 are the principal stress at a point in a strained material with Young's modulus E and Poisson's ratio this, then what is the principal strain? Okay, so principal strain in x direction, epsilon x, let us say this is the principal strain. Okay, so, or let us just write down epsilon 1. So epsilon 1 will be equal to sigma 1 by E minus mu sigma 2 by E minus mu sigma 3 by E. Okay. Now sigma 3 is not given. Okay. So two-dimensional stress is given. So sigma 3 by E, this will be 0. Sigma 1, let us replace by P1 as given in the question. So P1 by E minus mu P2 by E, P2 by E. Okay. Now E we will take common. Even in principle, sign is not given. Okay, so we'll consider both as tensile. So we'll put P1 and P2 both as tensile. Okay, now let us change. Okay, so E will be common in both, and let us replace mu by 1 by m. So P1 upon E minus P2 upon me. So we'll be getting P1 upon E minus P2 upon me. Yes, this is the correct answer. So option C is the correct answer. No need to further. Okay, so option C is the correct answer. Yes. Next question. The failure surface of a standard cast iron. Cast iron means ductile material or brittle material? Cast iron is brittle material. Okay, so cast iron is brittle material. So brittle material is subjected to torsion. So when brittle material is subjected to torsion, which type of surface we'll be getting? We'll be getting a rough helicoidal surface like this. Rough helicoidal surface at 45 degree. Okay, the surface helicoidal at 45 degree to the axis of the specimen. Correct answer will be option A. Option A will be the correct answer. Yes. Okay, next. Okay, so these are all the questions. So we have covered up to ESE 2006 questions. So up to ESE 2006 we have covered till now. So in last class we had covered up to from 1995 to I think 2000, and from in this class we have covered from 2001 to 2006. Okay, so this much questions we have covered, and now the next class will be on Monday. So this is an important change in the schedule. Okay, so schedule, let me tell you, from now on we'll be having Tuesday, Thursday and Saturday. Tuesday, Thursday, Saturday. This will be the schedule. Okay, so maybe this Saturday I'll have to go somewhere out. Okay, so maybe this Saturday will not have class, but you keep a check. Okay, maybe this Saturday we will have or we will not have, that is not sure, but definitely we'll be having classes on Tuesday, Thursday and Saturday. Okay, so from next Tuesday, Thursday, Saturday will be the regular classes. Okay, okay, so I'll take class on Saturday. Okay, Saturday I'll take class. Okay, I'll take class. There will be class on Saturday also. Okay, don't worry, class will be on Saturday. Okay, so I'll be taking class on Saturday and we'll be having classes on alternate days, Tuesday, Thursday and Saturday. Okay, so see you in the next class. Bye bye.